I will start with a different argument. So if you remember linear discriminant analysis, we assumed that we had a Gaussian density for each class. So let's say if I have a one-dimensional feature space X, what we did in LDA was that we assumed, or in linear or in quadratic discriminant analysis, we assumed that we had a Gaussian for the class 1 and another Gaussian for the class 2. And one way to represent this problem is by saying that we take a difference between these two. And then we will have overall a function that crosses the zero line somewhere here, and that would be our prediction. Now, a non-parametric way of doing that would be to say, no, we don't force a Gaussian kernel on each class, but we take a kernel density estimate. So let's say I have observations of the positive class here, and I have observations of the negative class there. And I now put, we will discuss this in more detail, essentially I put a bump on each of these points, and I thus obtain a density estimate for my one class, and I obtain a density estimate for my other class. And this small inflection that I've drawn here was on purpose, so this doesn't look Gaussian anymore. This is to say that in principle, this could take more complicated shapes if our data have a more complicated distribution. And one way to extract a classifier from this is to say, okay, we take the positive class minus the negative class, multiply it with priors perhaps, to come to an overall, or to come to a difference of class densities. So I could take the difference between the two and say it's a function that would look something like that. So this thick blue line that I've drawn here was the probability of any feature X given my positive class minus the probability of any feature X given the negative class. And well, the decision boundary would be at the zero crossings. So here would be our zero crossing, this would be our decision boundary. Well, and now look again at the formula for the radial basis function SVM. Sorry, I wrote it there. So alpha I are the Lagrange multipliers, yi are the labels, and then we have the kernels. So again, I can draw a one-dimensional feature space, and in this one-dimensional example, I'm copying the same data set that I had at the bottom. If I don't require a particularly large margin, I would have two support vectors here. One support vector for the positive class and one support vector for the negative class. And well, these kernels are now Gaussians that are centered at the support vectors. So I would center one support vector or one Gaussian on this support vector here, and I would center another Gaussian on that support vector there. And because I'm multiplying here with the sign, which is +1 for the positive class and -1 for the negative class, I obtain another Gaussian here. And well, if you now take the sum of the two, adjust it if necessary by this bias B, you again obtain some function, which I can try and plot here. Something like that. So the function that I've plotted here If you wonder what this is, it's a guy selling ice cream downstairs. Okay. So this is an RBF-SVM in a very graphical presentation here in a 1D specific case, whereas down here we had a kernel density classifier. Now this kernel, sorry, it's not the same as that kernel. The kernel down here in the kernel density classifier, it simply means we put a bump on each of the observations. Now the point is that here we put a bump on each and every one of the observations. So every point is a support vector if you so wish. Whereas in the example up there, only our few support vectors get a bump. So in essence, we estimate a function similar to that one here, similar to the difference of class densities, except that we focus our modeling effort really on the decision boundary. So we don't waste any effort on those points that are not support vectors. Typically, yes. People use other functions, but it's a Gaussian or something very similar to it. Exactly. All right. So that much for a review. And I now want to talk about kernels for different kinds of data. And I'm following a review by Gärtner from 2003 here. In essence, what do we need? Kernels should reflect the similarity of two observations. And the kernel matrix or the gram matrix should be positive semi-definite. Now these are the only requirements that we have, and you can now, conjure up all different kinds of similarity measures. In particular, we looked at things like, the RBF kernel, but consider the following situation. Let's say you have a speech recognition system, and the observation that you get is a function of amplitude over time. And we now have a reference measurement. So somebody said, for example, a number. Let's say somebody said the number 1, and if you take a microphone and if you look at this, you will get a waveform. Let's say a waveform that looks something like this. And now let's assume that this would be a reference measurement. Or in other words, a support vector for us. And let's now have a query. And let's assume that somebody did say 1, but he said it much faster. So my signal ends already here, whereas the original signal extended up to there. Now, the first thing is a vector. The second thing is also a vector, but if you remember the RBF kernel, we take a difference between two vectors. And this assumes that the vectors have the same dimensionality, but that's not true here. Maybe these were, 1,000 samples in time, and this signal already ends after 600 samples. Now, one way, of course, would be to fill this up or to zero pad this until we have, the same length thing here. But if you really want to compute similarities, if one signal is just a stretched version of the other one, that is not the best possible idea. So this is not going to work very, very well. So do you have a suggestion what you would do with that kind of signal? Yeah. So you would try and find the optimum alignment. Okay. And by stretching or compressing, now there are many, finding optimal alignments is a big field of research in itself. And what you could do would be, for example, to use dynamic time warping. You don't need to, remember this in detail. I'm just giving this as an example here. This is something that, as the name suggests, can be computed with dynamic programming, and you get out a cost or a distance, and you could then convert this into a similarity. For example, in the language of Gärtner, this would be, for example, a syntax-driven kernel. Go ahead. If you want to do this kind of alignment, I don't think that Earth mover's distance would be the best choice. It really depends on how strongly you want to penalize compression. But it could be that the Earth mover distance, let's say between this signal and that signal, where both people said, in words, said 1. It could be that the Earth mover distance between these two is much larger than between somebody who said the number 2, but took the same time as that one. But in other instances, so if you really have histograms, then the Earth mover distance would be a good choice, for example. Yes. How would you parameterize this with support vectors? The thing is that this entire thing is a support vector. So yes, you would have, some abstract. Well, we're working in the dual, so all I need are the kernels between one of my reference measurements and the query. But conceptually, what you have is in some abstract space utterances. This is now an abstract feature space where people said 1 and other people said, go away, or they said leave me alone, or they said 3, or so if you have one of these, if you're trying to build one of these automated telephone systems, you can expect a lot of these. Leave me alone, give me a real human, and so on. Yeah. Okay, but conceptually you have that where each of these utterances is now some amplitude signal as a function of time. But if we work in the dual, we don't use these explicitly. Instead, we only need the similarity evaluated between any of my existing measurements and the new measurement. Okay. Now, You mentioned Earth mover's distance, and indeed, histograms are an extremely important type of or are an important means of summarizing your data. And for histograms, you could use, for example, the intersection kernel, which I'm not sure how to write this. If I have a histogram of a sample I, and I have a histogram of an observation J, you then loop over all components K and take the minimum of these for any of the P bins that the histogram has. So let me put this in words, and I hope that with words and formula it will be clear. So given histograms with P bins, and my histograms here I called them HI and HJ. You can take the bin-wise minimum and sum over it. I've forgotten the sum in the formula. So and you can show that this is positive semi-definite by using the following representation. If I have a total of n observations, I can construct the following type of representation. I first use n indicator variables for the first bin, and then I use n indicator variables for the second bin, and then this goes on until I have n indicator variables for the pth bin. And now I can do the following. For my first histogram, for histogram I, let's say for example that I had a count of 3 in my first bin. Then I would put 3 ones and then fill the rest with zeros. And let's say that in the second bin perhaps I had just a single count. And well, let's say that we had a count of 4 in the last bin. This would be not a very compact, but it would be a representation for histogram number I. And now I can do something similar for my histogram J. So let's say histogram J only had a count of 1 in its first bin and had a count of 2 in the second bin. And let's say it had nothing at all in the last bin. And there are some bins that I have omitted here. And you can now take that as a vector. And you can take this, or let me not transpose it. Let me transpose this one here. And if I now multiply the two, you will see that only those places where I had 2 1s will survive. Okay, so this will give this thing here is a redundant representation of the formula I had up there. And look, this is an inner product in this funny representation, and an inner product will give me a kernel, or the inner product of two vectors gives me something that's positive semi-definite. So this is just to show, this kind of construction here is used just to show that the intersection kernel corresponds to an inner product in some funny space. And as such, it is a valid kernel. And I want to argue why histograms are so important. I've taken a slide here from Brendan Fry showing the performance, or showing a scheme of what the UI/UC NEC team did in 2009 to win the Pascal classification challenge. That's a pretty difficult problem where you have 20 classes of objects. And here's what these authors did. They take a picture, then compute a so-called dense sift feature map. So in essence, for each local image region, they compute a orientation normalized histogram of local orientations, and they then summarize all of these many histograms for different subparts of the image. So overall, they end up with a histogram with a total of 8,000 entries that summarizes the contents of an image. This is it's like a fingerprint. This histogram is a fingerprint of that image. And similarly, you can compute a fingerprint for any image that you're interested in. And then these fingerprints are fed into, in this case, a linear support vector machine to decide what is the right class. And then these authors, they went to some pains to optimize the features and to optimize the representation of the image, all of which is, by the way, unsupervised. So the image labels are not used until here. And then they used linear SVM in this very high dimensional space, in this 8,000 dimensional feature space. So you count in each of these tiny subregions you first find dominant local direction, and then relative to this dominant local orientation, you compute histograms of boundary strengths. It is a way of summarizing the local appearance of an image. It's not invertible, so if I give you this vector, you will not be able to reconstruct the image from that. But the good thing about it is that it's fairly distinctive, or the fingerprints that you find, if you put in different images or different local contexts, you get out quite different fingerprints, and this is what these methods capitalize on. And if you want to know more about this, you should come to the image processing lecture, where these kind of features are discussed in great detail. Okay, so that is so this question I didn't fully answer. Are there questions that I can answer for you? No, because I will run totally out of time if I explain more if I go into more detail here. Oh, could you switch, please? There. So the kind of representation that I showed on the slide is one kind of a so-called bag of words representation. And bag of words, it comes from the text analysis domain. And if you summarize a text in terms of a bag of words, you simply count how often does a particular word appear, disregarding, you know, the entire sentence structure and so on. Now I want to show you one more concept that I think is elegant and that you may come across at some point, namely the Fisher kernel that is representative for kernels that can be generated from so-called generative models, kernels that can be constructed from generative models. And I want to use the same example again of an amplitude and time, and let's say we have some kind of time series. And let's also assume that we have some kind of generative model. Sorry, this is terrible English, model by model, with a couple of parameters, which I'm summarizing here as theta. So for example, if we talk about such speech signals, typical model would be a hidden Markov model that we will discuss at the end of the semester. Now, one way to construct a kernel is as follows, namely to compute what is called the score of an observation, which is the derivative with respect to all parameters of the likelihood. So we have the derivative of the log likelihood at some observation x. And we can now compute a kernel for a query point x and a reference observation xj. Where I'm doing one more thing, namely I am in the sense of a Mahalanobis distance, I am computing something like a skewed distance here, where I is the Fisher information matrix, the expectation of the score evaluated for a specific parameter set. So it's the expectation of the score, the outer product of the score with itself. And you see, if I omitted this part here, it would simply be an inner product between two scores. And taking the inverse Fisher information matrix here is a means of correcting for the magnitude of the gradient that we may have for different parameters. So for example, if the Fisher information matrix, if I represent it here as a covariance matrix, normally if I had two vectors, let's say this one and that one, if I ignore this inverse matrix, well, I would simply take the product between these two vectors, but this matrix tells me how I should scale them before taking their inner product. Now, what is the interpretation of this? Essentially, this tells me in which direction a new observation wants to pull the parameter vector theta. So when I train the model, for example, by maximum likelihood, I want to make sure that the model explains all observations well. And if I now increase the weight of a new observation or of an observation, or if I introduce a new observation, if I were to re-optimize my model parameters, I could look at it in the sense that each observation pulls the parameter vector in one particular direction. So let's say, for example, that we want to train a hidden Markov model for people saying the number 1. And now I have different training instances. I have the training instance that I've drawn here, and I have a second training instance. Let's say somebody who said it faster. Now, these may be hundreds of samples, but my hidden Markov model has only, let's say, tens of parameters. And these different observations here, they favor different optimum settings for the parameters. So in that sense, they pull the parameter vector in different directions. And the Fisher kernel checks if observations x and xj, if they pull the parameter vector in the same direction or not. If we have a good model, so a model that fits these observations, and if both observations want to modify the parameter vector in a similar direction, then we can assume that they're similar. Okay? Now, overall, what happens is that we go from data that does not necessarily have a fixed dimensionality to a representation, namely this one here, which has a fixed dimensionality, namely the dimensionality of the score is the number of parameters that I have in my model. Yes. Yes. So you first optimize the model, and you then, you see, if you don't optimize the model, so let's say this is now an abstract space, let's say this is the abstract parameter space, and this is where the individual observations would like to have the parameter values, ideally. If I start with a poor parameterization, let's say I set both parameters to 0, then all observations will look pretty much alike. But if you have already optimized your parameters so as to lie, in some sense in the middle of your observations, then you can check if two observations pull in the same direction or not. Okay, so I mentioned as generative model here the hidden Markov model. Again, this is a model that's actually important for speech recognition and such, that we will talk about at the end of the semester. But I wanted to show you already here how this can be used to construct kernels for support vector machines. Okay, then I would like to make a break at this point, and after the break I will talk about how to combine multiple kernels and how to approximate nonlinear kernels. I talked about a couple of kernels, and you will rightly ask which is the right one. Well, given sufficient data, you will have an extra validation set, and the right one is the one that gives best performance. But that doesn't help you, if you're data starved, as often happens, if you're starved for labeled data. And there is one approach that tries to deal with that. It has been a pretty active area of research also, called multiple kernel learning. And if you want to read up on this further, there's a paper by Gönen and Alpaidin in JMLR 2011. And they classify no less than 98 multiple kernel learning methods. Okay, and you will now benefit from my page-and-a-half summary of this field. The motivation, generally speaking, is to do not put all your eggs in the same basket. This is stealing their words. So, like when I don't know if you have any shares, but typically you wouldn't want to have shares from a single company only. You try to somehow diversify your risk. And this is one justification for using more than just a single kernel. This is what multiple kernel learning is about, so how to combine multiple kernels. Also, you may want to let the algorithm pick the right basket, or at least pick the parameters of such a combination. Sometimes your data might have different aspects, and different kernels may reflect different aspects of similarity. And finally, different kernels, they may be using inputs from different representations. So let's say, for example, that you want to build a speech recognition system, and one that uses not just a microphone but also a camera. Then you will have, you'll have people saying one or other things, and on the one hand there will be the camera, and on the other hand there will be the microphone input, and you may want to use different kernels for the images, or separate kernels for the images and for the voice signal that you have recorded. And if that is the case, that you're combining data from different representations, then this has also been called an intermediate representation, or intermediate combination, sorry. Well, if there's intermediate, then there must also be a high and a low or something like that. Indeed, the field also talks about early combinations or late combinations. So an early combination would be to simply concatenate all the features. So in the example that I've just used, for early concatenation, you would take your 1,000,000 pixels from the camera, plus you would put your amplitude in the 1,000,001st pixel, except that the temporal sampling won't really work because you get perhaps 30 frames per second, but you record thousands of signals per second with your microphone. But anyway, early combination would be to simply concatenate the features, whereas a late combination would be to pool the decisions that are made by individual classifiers. So in the example that I used, you would have one classifier that is lip reading on the images and trying to figure out which number has been uttered, and you would have a separate classifier on the audio data, and then you would somehow pool these decisions. That would be a late combination. And in that sense, between these two extremes, to combine the input from different kernels would be an intermediate combination. And there is a large number of algorithms, as I've said, but these can be summarized in a few approaches. The paper uses 5 categories. I'm only giving you the 3 most important ones here, namely fixed rules. In the exercises, you already studied how you can combine valid kernels to produce new valid kernels. For example, if you sum positive semi-definite kernels, the result will be positive semi-definite. It turns out also that if you multiply positive semi-definite kernel matrices, the result will again be positive semi-definite. So a fixed rule would be, for example, to sum or to multiply all the kernels that you're interested in. Then there is an optimization-based approach where you take, for example, a weighted sum rather than a plain sum, so a weighted sum of kernels, and then you learn the parameters. So in this case, you learn the weights from your training data. Well, this makes for nice optimization problems, but they're harder, or even harder than the normal SVM. And then there are heuristics. There are many different heuristics. I want to mention only one, which is based on the kernel alignment. So the ideal kernel I briefly discussed last week. The ideal kernel matrix is given by y transpose, where y is the vector of labels for all of your observations, and the labels are +1 or -1, such that if you order all your observations such that you have all the observations from the one class first and all the observations from the other class next. You would get a block diagonal matrix with plus ones on the diagonal and minus ones everywhere else. So in other words, the ideal kernel will make all the members from one class very similar to each other, or very similar amongst each other, and will make them very dissimilar to all the examples from the other class. Now, this kernel alignment A is defined as follows. So given some kernel matrix K and given this ideal kernel, you would first take the element-wise product of your kernel matrix and of the ideal kernel matrix, and then you sum over it. So 1 here is it's a vector of all ones. And then you normalize, excuse me, as follows. So you compute the alignment between the kernel with itself, and you compute the alignment of the ideal kernel with itself. Take the square root of the product. And the alignment of the ideal kernel with itself, you can compute it. This is just n squared, and then you take the square root, so that overall gives the following expression. The numerator stays the same. All right. To the power of a half. So this is the definition of a kernel alignment. This is Cremonesi 2003. And now a heuristic suggests to use normalize alignments as weights in a sum. So e.g. compute the kernel alignment and normalize these to obtain a weighted sum of kernels. And the weight of kernel number m in your expansion would be the alignment of the mth kernel with the ideal kernel divided by the sum of the alignments of all other kernels. So there is nothing, this is not derived from first principles. This is just something that can be motivated and that is useful in some examples. Now, which one should you use? Of course, the nicest math you find in approach number 2. I think in the real world, you want to use those fixed rules. So in particular, if you use nonlinear kernels, if you use RBF kernels, it seems that simply taking the sum of these works pretty well. So if you want to write a paper, you should do that. But if you just want to use it, I would say use 1 with a variety of kernels of different width. So that, let's say, RBF kernels. So last time I talked about cross-validation and model selection and so on. So there we, according to that scheme, we would have used a single RBF kernel and would have cross-validated to find the optimum width of the single kernel. And if you want to use multiple kernel learning, then a good idea is to simply use a sum of RBF kernels that have a different width. Now, and if you ask me what method works best in general, unfortunately there's no answer. It really depends on the data set. So there's always a little bit of empiricism involved if you want to tickle out the last few percent of performance in any given classification task. Okay. Everybody happy with that? Reasonably. Okay. Then I would like to tell you how nonlinear kernels can be used with linear SVM solvers. Which sounds a bit like a contradiction. After all that we have heard about the kernel trick, well, you would expect that we work in the dual and that's it. Now, in the real world, the linear SVM solvers have been very popular in recent years. And there are perhaps two reasons. One is that representations like the one that I mentioned for the images sorry, I need to plug this in. So representations like this one here, that they are very high dimensional. Yeah? So you work in an 8,000 dimensional space, and according to the function counting theorem, if you work in an 8,000 dimensional space, there's a very good chance that you will be able to, really linearly separate your observations. And then I think it's for reasons of numerical efficiency, because in the last 5 years or so, some very fast solvers have been published for linear support vector machines. And the solvers in principle could be made to use kernels, but in practice some of the tricks that they use internally will no longer work as well. So I think a motivation here is that we have very fast solvers for linear SVMs. And they typically operate in the primal domain using, for example, gradient descent. There is a method called Pegasus, or I've previously mentioned SVM Perf, which uses a so-called cutting planes approach. So in cutting planes, you start with a suboptimal weight vector W. You then look for samples that violate your constraints. You add these to your definition of the problem. You solve again, and you keep doing that until you're happy. Which is also kind of gradient descent, essentially. Now, I'm referring to a paper in this entire part of the lecture from Rahimi and Recht, which came out at NIPS 2007. And these authors propose to approximately explicitly map the points to higher dimensions instead of using the kernel. So Rahimi and Recht say that instead of using a nonlinear kernel, as suggested by the kernel trick, you do the projection explicitly, however only to an approximate space. Or let me say, project explicitly, but in an approximate fashion. And it's an approximation in the following sense. So let's say if we use a polynomial kernel, you have to specify what maximum power you take in your polynomial, and depending on the power you use and depending on how many features you had initially for your observations, you may get a feature space of say 10,000 dimensions. And this is why I argued last time that it's good to use this kernel trick, because you don't want to take inner products all of the time in 10,000 dimensions and so on. However, if we can get similar values out numerically in, say, only 50 dimensions rather than 10,000, then that would be an interesting compromise. Okay, and this is about how to find such a compromise. They evoke Bochner's theorem, which says that if you have an appropriately scaled, positive, semi-definite kernel K, the Fourier transform is a probability density. Yeah, so by scaled, I simply mean that you have multiplied it with an appropriate scalar number such that the second part of the sentence is true. A probability density is non-negative and integrates to 1. And by appropriately scaling your kernel, you will make sure that it integrates to 1 and not to some other number. Now, if you read up on Bochner's theorem, you will find more mathematical language used, but essentially it is that. And note, by the way, that positive semi-definite is not the same as positive. Okay, so I could imagine, to take a famous example, I could take the sink, for example. So let's say this is sink. And if I Fourier transform it, I get out something that is strictly non-negative. So this is a low pass in the frequency domain and in the spatial domain. So by the way, this tells you that that would be an admissible kernel. It would perhaps not be one that's very intuitive for us. So it would tell you that for two samples that are very close nearby, you get a high similarity. And as you increase the distance, the similarity drops. And then they become dissimilar, and then they become similar again, and so on. So these oscillations are hard to explain, but it's a valid kernel in the sense of being positive semi-definite. For those of you who know about signal processing, you wouldn't think about Bochner's theorem, you would think about the Wiener-Khinchin theorem. Okay, so the sentence here, I can write that as a kernel, and I'm now assuming that it's a shift invariant kernel. So I'm not writing xi comma xj, but I'm saying that the value of the kernel depends only on the difference vector here. And I'm taking the Fourier transform of what should be a probability density function. So I'm using nu for the frequency domain here. J is the imaginary unit. And this is again my difference vector. Okay, so we just have the Fourier transform here, and the statement is that if my kernel is positive semi-definite, then P of nu must not be negative, and if I scale it appropriately, then it's also true that the integral of this density is 1. Now, the kernels that we work with are typically real and symmetric, and if the kernel that I'm interested in is real and symmetric, then I can simply use the cosine transform instead of the Fourier transform. So if it's symmetric with respect to the origin, then I can write that the kernel of xi minus xj and now rather than using these complex exponentials, I am simply using here a product of two cosines. So that holds if the kernel is real and symmetric. But under that condition, this is exact, no approximation here. Now, we have some function here that's weighted with a probability density function, and if you remember how to compute the expectation of some function of a random variable x, if it's continuous, then this would simply be p of x times f of x dx. Okay, and you see we have a probability density here and we have a probability density there. So in other words, that means I can rewrite that as an expectation. I can say that this is the same as expectation with respect to frequency here of the following. And that is also still exact. And now comes the crucial approximation, namely, you know, if we're interested in an expectation, like if we want to have the mean of a function and we cannot compute it analytically because we don't have the true density, we only have samples that were drawn from the density, then what we do is we approximate this with a sum. Yeah? So we say, for example, my estimated mean is simply the 1 over n times the variables that I have sampled from a distribution. So that would be here if f is the identity function. Okay, so I'm using the same approximation here. So I'm saying this can be approximated with, I'm drawing here, let's say Q samples. where nu is are realizations of a random variable that has a probability density function p of nu. So I've tried to make this very explicit here for the case of a Gaussian kernel. So let's say I want to compute the radial basis function kernel. If I Fourier transform the Gaussian kernel, I obtain the Gaussian. And this is what I tried to plot here. And now if you look at the last formula that was on your slide, we take the integral of the product of this density with a cosine term. And now the cosine term, that this is a plane wave, and its direction and frequency depend on this distance vector. So I've plotted a coordinate system here. The origin is there. And in this case, the difference vector xi minus xj was pointing here. And this determines the direction. So this is the normal vector of this plane wave and the frequency. So in particular, if I picked a larger difference vector, I would obtain a higher frequency plane wave because I multiply this thing here. And well, if my difference vector points in a different direction, then this plane wave here rotates. Okay, now if I multiply this with that, I obtain a thing here, which I integrate over. And well, qualitatively what happens, let's say we are interested in the RBF kernel between two samples that lie very far apart from each other. So in that case, I would have a long difference vector that would give me a very high frequency modulated plane. And if I now integrate over this very high frequency modulated plane weighted with such a big smoothing function, I will obtain something that's very nearly zero, as you would expect. Huh? So if the RBF kernel, if you query it at points that are very far apart from each other, it gives you values close to zero. And now the approximation, the last equation that we wrote, was to say that rather than computing the integral over this function here exactly, we approximate the result by taking a few random samples. So you see, if I take the integral, well, I integrate over this entire domain. If I, let's say, if I replace the integral with a summation to get a first approximation, I would still have to take all the points, which would still be very many. And now the suggestion here is to not take all the points from the domain to approximately compute the integral, but to only sample a few points from this density here. And I've done this. So sampling a few points gave me these plane waves that travel in different directions, but they're all of pretty or of relatively low frequency. Well, and then I query these traveling waves at a location that I've marked with a red dot at my difference vector, xi minus xj. And I here show you the approximation of a Gaussian kernel that you can obtain in such a way using 1, 5, 10, or 50 random samples. So at least on a computer screen, you will see that even here, this is not yet perfect. So I have a little bit too much density here, and I have a little bit too much density there. But, you know, it starts to look like a Gaussian. And this is what we wanted. We wanted to have a Gaussian kernel. Notice that here, you know, even already for two, so this is a single cosine. And even if we take, let me check, was it 5 or 2? Yeah, it says 5 in the legend, but I wanted to look in the code. Yeah, 5 is correct. Okay. So even when you take only 5 samples, so you add up 5 plane waves like these, you already obtain something that remotely looks like a Gaussian. It's still a little bit skewed, but even so. All right. Can we go back to the paper, please? So what you see here already very much looks like an inner product. So I can say that this is an approximate high dimensional mapping of my point xi and an approximate high dimensional mapping of my point xj. And I can write these down explicitly. Okay, where again all these nu k are realizations of a random variable that has this density p of nu. Well, and you can do this for any kernel for which you can compute the Fourier transform and from the Fourier transform of which you can sample, which is possible essentially for all kernels. In their paper, the authors do it explicitly for the Gaussian kernel or the Laplacian kernel or the Cauchy kernel. So what's the bottom line here? Instead of using the kernel trick, we let me put tildes here to say this is not the exact embedding. We can explicitly embed the observations in a higher dimension Q such that the inner product between observations that have been embedded in this fashion approximates the exact kernel function. Well, and then you can use a linear SVM. This is perhaps wild. Go ahead. So in this higher dimensional space, you explicitly represent the observations by phi tilde of x, and then search for the best hyperplane in this q-dimensional space. And q was the number of points that you sampled. So the important line, so note that we have kernel here, and we have that, and we have an approximately equal. So you know which kernel you want to use. You know for which pair of observations you want to compute the kernel value, which is just a scalar number. You then compute the Fourier transform of your kernel. You sample q points from this Fourier transform. These q points are called the nu k. And the sampling you do just once, so no matter which points x you insert here. And you then build these, so this thing here, this is a plane wave, and you evaluate it at this position xi minus xj, and you sum over all these plane waves. And Bernard, can you show the picture once again? So the dimensions that I plotted here this time, they are the dimensions that I used here are xi minus xj. So the origin is here, and I've plotted using, so let's say here it's using just 5 points that were randomly drawn from the density. I'm plotting the approximation to the kernel for all possible difference vectors in the plane. And you know what you expect. This should be a perfect isotropic Gaussian, and this is what we find empirically. So in this case, I had to map to something like a 50-dimensional space in order to get a good approximation. Can we go back here, please? So this summation here, I can write as an inner product. And here I gave explicitly the coefficients of these vectors in this q-dimensional space. So rather than work with my original observation x, I now work with phi tilde of x, which I can compute explicitly, and then this is my new primal domain in which I can use a linear solver. I did use a Gaussian kernel here. Yeah. Yeah, so let's come to this statement about uh, the implicit dimensionality of the Gaussian kernel. And what the textbooks say is that you map implicitly to a space of up to an infinite number of dimensions. However, the actual dimension that's realized is of course always limited by the number of points that you have in your training set. So the actual implicit dimension is number of training points minus 1 or something like that. Because you know, if you have 3 points, you can span only a plane. And if you have 100 points, you can only span a 99-dimensional space, not an infinite dimensional space. So these points, you know, they may be in principle embedded in an infinite dimensional space, but they live on a subspace of the dimensionality that I have given. Okay, so the training points always lie on a subspace whose dimensionality is given by the size of the training set. And the dimensionality is given by the rank of the kernel matrix. So in principle, if you take a very narrow RBF kernel and if the observations do not lie on top of each other, an extreme kernel matrix that you would get would look as follows. You would get ones along the diagonal and 0 everywhere else, meaning each observation is only similar to itself and far away from all others, or let's say, you know, approximately 0 here. And if you now add a new point, so this is my kernel matrix K, and if you now add a new training point, you know, it will add a new diagonal element and will add new zeros on the off diagonal. So each new observation can increase the rank of my kernel matrix by 1. And that's why if you have a sufficiently narrow RBF kernel and the points do not lie on top of each other, then as your training set goes to infinity, then the dimensionality to which you embed also goes to infinity. Now the actual dimensionality will depend on the size of your training set and then also the width of these kernels. Because if the kernels are very wide, then you start to introduce more linear dependence here, and then the matrix may become, you know, may not have full rank any longer. And so if you use this scheme here, let's say even if you have 1,000 points, you would try and map them to only, you know, let me guess, some 50 or so dimensions. Well, this was perhaps a bit, let's see, they will have tables somewhere. This is the Rahimi and Recht paper. And somewhere they have the number of features they use. No, I don't see it. Okay, so here you see the original dimensionality of different data sets. And these numbers D and P are, I think, the number of points they sampled randomly. So the dimension to which they map implicitly. And I'm not sure for which kernel this is now. I think maybe for the Gauss kernel, but I would have to check. Okay, so here in these big cases, you would have 5 million instances, but you map them to only 50 dimensions. So I've mentioned this because this random approximation of, or this approximation using random projections, that's something that's starting to find a lot of interest in pattern recognition. So I thought this is one use case where we can see that sort of technique in action. More immediate questions? Yes. No, I'm assuming it. And well, most, not most, but you know, many kernels that people use are shift invariant. So you say the similarity only depends on the difference vector, not on the absolute position. And by the way, Rahimi and Recht, they have an extra bias term in there, but I think you don't need this for real kernels. More questions? Okay, then let's have a break, after which I will talk about the one class SVM and how it can be used for outlier detection.